Weather. One of the most astonishing forces on Earth. Capable of both devastating power and spectacular beauty. Wherever you live on the planet, weather shapes your world. Yet for most of us, how it works is a mystery. To really understand weather, you have to get inside it. So I'm going to strip weather back to basics.
All in the name of science.
Uncovering its secrets in a series of brave, ambitious, and sometimes just plain unlikely experiments.
Well, it certainly feels like a dust storm from here.
To show you weather like you've never seen it before. Water lies at the heart of our weather, but not just as rain. Because water can transform itself, redefining its powers in the process, creating the fastest, the slowest, the softest, and the hardest weather on Earth. Often changing from one to another with alarming speed and striking consequences. In this program, I'll reveal water in all its shapes. I'll capture a cloud.
Okay, little cloud, let's see what you got.
To see just how much it weighs. Discover why hailstones are able to do so much damage.
Oh, look at that.
Find out what would happen if rain fell in one big lump.
It's amazing, isn't it?
And I'll experience water in its most ferociously powerful form, as an avalanche.
Speechless. Genuinely speechless.
All our everyday weather appears to come from the clouds. They're the best clues most of us have as to what the weather is likely to do next. They dictate if it's sunny or dull. And they're where all our watery weather seems to come from. But how? What exactly is a cloud?
Come on, you've done it. If not, you should. Gazing at clouds, dreaming up shapes. And the next time you do, 2 things you should know about clouds that might just change the way you think. Number 1, clouds are really heavy. Even that fluffy little cumulus could weigh as much as 2 elephants. And secondly, because of that weight, all clouds are falling, slowly, steadily, down to Earth.
I know, both those things sound pretty unlikely. Which is why I'm going to put them to the test. And I'm going to start by trying to discover just how much a small cloud really does weigh.
Now, I know I'm not the only one who, when presented with a sign on a bench saying wet paint, has to touch the bench just to check it really is. So when I heard that a cloud can weigh as much as 2 elephants, but I had to check it out. The only thing is, it turns out that weighing a cloud is a bit more of a faff than checking to see if paint is wet. Obviously, you can't just hang a cloud off a spring balance or pop it on a set of scales, but you could measure the moisture in it and work it out from that. So I thought, what if we could fly a giant ball of cotton wool into the cloud to gather the moisture? As an idea, it needs a bit of finessing, yes, so I've got an engineering mate of mine to iron out some of the wrinkles, and he came up with this.
Okay, so it's not actually cotton wool. It's an industrial version. Ceramic wool. And it's not one solid ball either. My friend reckoned that by making the centre hollow, it would double the amount of wool that came into contact with the cloud. He calls it his sky sponge.
And then we've got that to put it in the cloud. It's all fairly standard stuff.
So, first off, let's check how much this sky sponge weighs dry. That's 37 kilos, which for a sponge is already pretty heavy. But we need that weight to be able to fly it accurately, especially when the pilot is someone not that used to carrying freight. I know, it's not a good start. But as nobody has ever done anything like this before, I'm as good a choice as anybody. In the end, it was deemed not a job for an amateur, no matter how enthusiastic. So I took a co-pilot, Andrew, with me to keep an eye on things, mostly on me.
So, helicopter, check. Basket full of highly absorbent ceramic wool, check. All I need now is a nice little cloud to dip it into.
And that's not as easy as you might think. Because when you get close to them, clouds are, well, they're enormous.
You look at them from the ground, they all look perfect and fluffy and small. Get up and they look entirely different. I've got to find a nice individual one, drop it in and see how much water it pulls out of it. I'm assuming it won't soak up the entire cloud and we'll be left with underslung the weight of 2 elephants. That'd be bad.
A full-grown African elephant weighs on average 4.5 tons. A quarter of that would pull my helicopter straight out of the air. But if I just weigh a fraction of a cloud, then multiply my results, it should give us some idea how much a whole cloud actually weighs.
Pick a victim.
What about the one in front up here?
Yeah, that's a nice one. Right, cloud has been sourced. It is quite important that the helicopter itself doesn't go in the cloud. You have to remain visual with, well, pretty much everything.
I need to fly low enough to dip the sky sponge into the cloud, but high enough to keep the chopper above it. Which is trickier than it sounds. Well, for me.
Oh, great. Well, that's all round bad.
First time round, I missed the cloud altogether.
This is a fairly unusual exercise, cloud collecting.
Yeah, that's my excuse anyway.
This one will do a treat. Okay, little cloud, let's see what you got.
Close up, the cloud seems so wispy, it's hard to imagine we're going to soak any water up at all. Okay, we dipped it. Let's get this thing down and see what we've got. Well, It's wet, that's a start. But how wet? Have we managed to collect enough moisture to make a difference on the scales? We have 10 whole kilograms of difference. I know that doesn't sound like much, but look at the size of the cloud. Then look how much of it the sky sponge flew through. Just that small section had 10 kilos of water in it. If every section that size weighs the same, then that little cloud must be getting on for, well, not quite 9 tons, but a lot. And a good-sized thundercloud might be 10 kilometers tall and 10 kilometers wide, which would make its total weight more like 1,000,000 elephants. Or if you prefer, about 60,000 jumbo jets. So how on earth does all that weight stay up there? To find that out, we're going to have to build a cloud of our own.
Right. What I've asked to achieve here is an indoor cloud. What I've got is a cattle trough full of water, and I don't even know what these things are. Fortunately, what I've also got is Jim, who is an atmospheric scientist and can hopefully help. What is this? How's it going to work?
So this is how we're going to make something akin to clouds.
Right.
Obviously, it's not a cloud, but it's the closest we've got to a cloud making machine.
Right.
So what we've got in here are some ultrasonic humidifiers. So you quite often see these sorts of things at garden centres and things like that. They just produce very, very fine mist.
Garden centres. It's sounding less high-tech now, I'll be honest.
They're masquerading as nice ornamental devices,
Okay.
but secretly they're cloud-making devices.
Well, there we go. Well, come on then, make it work.
So all I need to do is turn this on.
Oh, hello.
There you go.
Suddenly, miniature clouds appear.
And that's just by breaking the water molecules down into smaller bits.
We're breaking the liquid water
Yeah.
into just very, very tiny droplets of water.
These garden pond devices turn the water into tiny droplets. And that is exactly how a cloud works. Clouds float because the water drops inside them are so small and so light.
What's the difference in size? How big is a droplet of this compared with a
So
droplet?
a droplet of that is 5 microns, but that means absolutely nothing to you.
Small.
Okay. So, but a rain droplet, you can get your head around the size of a rain droplet. A rain droplet's about 2 millimetres. So the difference in size between these and the rain droplet is the same as if you've got a sugar cube and a caravan.
Hang on, which is the caravan?
So the caravan is the rain droplet,
Right.
and the sugar cube is these tiny little droplets.
Right, well that is working.
The humidifiers have split all our caravans up into billions of sugar cubes.
Okay, lid goes on.
Okay.
But to really complete the effect, we want to see if we can get those tiny moisture droplets to float in the air.
We'll turn the fan on now, and we'll see our clouds emerge.
There it is.
Weirdly, it feels dry. Hard to believe our sky sponge managed to soak this stuff up.
So this isn't just something that looks a bit like a cloud, this is pretty close to a cloud.
But these are just droplets of water, very, very small droplets of water, and that's what a cloud is.
Jim, not being critical of your cloud, but it looks a lot more frantic. I think of clouds as just solid state, really, just drifting.
What you're seeing here is what's happening around the edge of a cloud. It's constantly changing.
So you get up close to a cloud and it's really quite busy.
Yes.
So whilst I'm very impressed with your homemade cloud here, it's kind of not up enough.
Now, this might look like overkill, But actually, our cattle trough is surprisingly heavy, just like the water in a real cloud. And I do need to get all that water off the ground to check that second fact. Are all clouds really falling back to Earth? Jim and I wait with bated breath. We might have made the water droplets small enough to float, but it's true. Once they're up in the air, they drift back towards the ground.
So this effect where I can see it rolling over the top and then sort of falling, that's accurate.
Yes, our cloud is dropping out. So if you look at clouds with binoculars or something like that, you'll see bits of streams of cloud.
So because this is small, it all looks faster. But if this were as big as a real cloud, this effect, this exact effect, is what's going on all the time.
Yes, just continuously, all the time, around the edges of clouds, around the periphery of clouds, we've got this process going on all the time.
So there you have it. Clouds are heavy, and they are all falling slowly down to Earth. It's just that most evaporate before they ever get there. In fact, the typical lifespan of a small cumulus cloud is only 10 to 15 minutes. But while they're up there, they act as a sort of public transport system for water, carrying it from one place to another. Until either the service goes off duty or they dump all their passengers out as rain. There are about 13 trillion tons of water being moved around in the atmosphere. And every day, about a tenth of that comes crashing back down to Earth. Sometimes these storms are incredibly intense. The quickest on record dumped 12 centimetres of water in just 8 minutes. The heaviest managed nearly 1.5 meters of rain in under 10 hours. And so to my home territory, where on average it rains 1 day out of every 3.
This is my favourite place in the entire world. It's in the Lake District, Honister Pass, running down to Lake Buttermere. I've been coming here for 27 years. It has one of the best views in the world. I've seen it once. That's because this specific place is the wettest in England. On average, 4 meters of rain falls here every year. And yet, on the one day when I am here specifically to talk to you about rain, it's not actually raining. We've had to resort to this.
Yes, sprinklers in the wettest place in England.
However, this will suffice perfectly to allow me to show you what I want to show you.
Puddles. Puddles hold the key to seeing how those tiny cloud droplets turn into raindrops. We can't look into a cloud to see how raindrops form, but we can get an idea of what's going on by looking in a puddle. As the raindrop hits, part of it is attracted to the water. What bounces back up is a smaller droplet, about half the size. When that droplet hits, the same thing happens again. Around half of it stays in the puddle. Now imagine that in reverse and upside down. The puddle is the cloud. A water droplet doubles in size by attracting other water droplets. These stick on in a process scientists call coalescence. It increases again and again until it's so heavy it falls away. And that is, roughly, how rain is formed.
It feels right like this. This is how it feels here.
Which is just as well, because I've got one more thing I want to tell you before I get them to turn these sprinklers off. And it's about the official difference between rain and drizzle. Look closely at a puddle's surface. If the drops are splashing, like here, then it is rain. But if there are no splashes, then it only qualifies as drizzle. Officially. Clever, isn't it? Splashes, rain. No splashes, drizzle. But what they've both got in common is that they're just too heavy to be held aloft.
We talk about heavy rain, but water is heavy, very heavy. To give us an idea of just how heavy, we are about to see what would happen if all of Borrowdale's 4 meters of water fell in one go.
Now, obviously, we can't get a digger the size of the Lake District. So we're just going to recreate what it's like when 4 meters of water hits one small area.
So we have 4 cubic meters of water in the bucket, which amounts to 4 tons at height. Then beneath it, you'll see we've found a car for scientific purposes.
Let's see just how much damage that amount of water can do. Looks like rain. Yeah, pretty brutal. But I shouldn't be surprised, because the water actually weighed 4 times more than the car underneath it. Every minute of every day, 900 million tons of rain land on our planet. That's about the same amount of water as in all 16 lakes of the Lake District.
Oh, they're going to notice. But it does prove the point. Water is really heavy. That is just the annual rainfall for Borrowdale, where I've been going on holiday all of my life. Explains something about it. It's amazing, isn't it?
Luckily, this could never happen with real rain. Not even in a tropical storm, where sometimes it feels that the heavens have literally opened. Partly because, as we saw earlier, raindrops fall the moment they get heavy enough. And partly because of what happens to rain as it falls. To show you what I mean, I'm hard at work building a sandcastle. And Professor Jane Rickson from Cranfield University is filling a plastic bucket from a pond.
There were always kids like you on the beach, weren't there?
Okay, so what's all this about? Well, pour water on a sandcastle and you completely flatten it. No surprises there. But rain doesn't fall from waist height. It falls from clouds that are at least 300 meters above the ground. And that makes all the difference. Let me show you by building another sandcastle and throwing the water off something just a little bit higher.
Now, obviously, this isn't as high as a real cloud. They start at around 300 meters. This tower is 30, but it's tall enough for what we want to do.
Okay, Richard, let it go. Idiot.
Yeah, wrong side. How was I to know? Let's try it again.
Okay, Richard, let it fall.
And so, another bucketful leaves the tower, but what arrives below is rain.
And there it is, still standing. So, why? Why is it if I throw the water from up there, you'd think it would smash it to bits even more, but it's still standing. What's the difference?
Well, what happens is you were throwing that water down, air resistance, the turbulence in the air is overcoming the surface tension of that lump of water, breaking it into smaller drops. Do you want to go and see that? Should we do it again?
Yes, I'll get the water.
As the water falls, it meets air resistance. And the larger the lump of water, the more resistance it experiences. That friction breaks the water up into smaller pieces, sometimes inflating the drops like parachutes before blowing them apart. The further they fall, the smaller those drops become, until finally they're so small that the air has little effect on them, and they land as rain.
So that's why the water landed in drops and didn't smash it, rather than a big bucket-shaped lump.
That's right. And in fact, you can actually see the point at which that lump starts to break up into those smaller drops.
Well, you can if I climb the tower again. It actually happens surprisingly quickly. Within 10 meters, there's enough air blowing on our bucketful of water to break it down into drops. If our digger had been just a few meters higher, then the car might well have survived. So even if it was possible for water to fall out of the sky in one big lump, by the time it got to the ground, it would still be rain. Because they break down like this, the average raindrop ends up about 2 millimeters across. But there is a way that water can fall out of the air in bigger, more dangerous pieces. By shape-shifting into ice. Now, most of us think that when we see ice falling out of the sky, it's hail.
So what if I told you this wasn't hail at all? Sure, it looks like hail, but it can't be hail. You can't get hail in winter. It only happens in summer. I know, you think you've seen hail in winter, but trust me, you haven't. What you've seen is this, ice pellet. Ice pellets are formed when a snowflake partially melts on the way down, losing all its pretty branches, and then refreezes, forming a small ball before it hits the ground. Just to make things even more confusing, in North America they call this sleet, which over here means a sort of slushy mix of rain and snow. Either way, This is not hail. Hail is something entirely different.
Charles Knight has been studying hailstones for the last 50 years. And in his refrigerated laboratory in Boulder, Colorado, he offers to show me exactly how hailstones are different by sawing one in half.
It's very simple. We just use a hobby bandsaw like this.
You're just going to slice it in half?
Yes.
How long have you had that hailstone?
Oh, about 10 years, actually.
What? But it's worth it. As soon as Charles opens it up, the difference is revealed. Hail is made of layers.
And there you can see one layer there anyway.
So where there's that little circle?
Yes. But in the bigger hailstones, there's much more obvious layering. This is an example of really what you would call a giant hailstone.
It's enormous.
It's enormous.
Yeah.
Yes.
But that's obviously not going to stop him cutting it in half, even though this one is 15 years old. Oh, wow! This time, the layers are crystal clear.
If you make a thin section, then you can really see the layering.
That's a slice right through it. That's absolutely beautiful. That's really telling its own story, isn't it? Just like the rings of a tree, these layers chart the story of how this hailstone grew. It's a story that starts with a thunderstorm. And thunderstorms only tend to happen in summer. Because of the height of thunderclouds, some of the water droplets inside them freeze. But the powerful updrafts created by the warm weather keep the droplets supported in the cloud, where they collect more water, with new layers freezing on in a separate shell. Until finally, there are so many layers that they're too heavy to be supported and they fall to the ground.
Which got me thinking, because it's made in layers, does that mean hail is stronger than a single solid ball of ice? You make wood stronger by laminating it. You make glass stronger by laminating it. So does laminating ice make it stronger?
Certainly, hail is powerful. It causes over £1 billion worth of damage a year. But is it any harder than conventional ice?
To find out, we're going to have to go into uncharted territory with an experiment that hasn't been done before, using that. Yeah, I know, it looks like a length of plastic pipe on some tables in a field, and to some extent, well, it is. But you should see what it's about to do to that table tennis bat.
Its inventors, Purdue University's Jim Stratton and Craig Zarin, wanted to see just how fast they could get an ordinary ping pong ball to fly. And the answer, using this contraption, turns out to be very fast indeed.
That is astonishing. This projectile is moving when it comes out of there.
Oh, yeah. About 919 miles an hour.
Oh, that's brisk, isn't it? Yeah. So you brought along your device, which is, if you think about it, a sort of nightmarish automatic serving machine, and you've agreed to help us.
Mm-hmm. Yeah.
Okay, right. So here's the plan. We're going to see which is harder, ice or hail. But first of all, we've got to make some hailstones.
We've already seen how much of a faff that is, even for Mother Nature. But luckily, Jim and Craig have a plan. A plan that starts with dry ice.
It's like an 80s pop video.
A pop video starring a bead on a bit of string. The dry ice makes the bead really, really cold
2 rolls.
Yep.
before it's dropped into cold water.
If you'll notice, every time he puts it in there, you can hear just a little bit of a crack. You can hear a little bit of fizz, and that's the water instantaneously freezing to the outside.
So that's 1 layer of ice around that little
Very
seeding
small layer,
leaf.
yep. Very small layer.
How long does this take?
About 10 minutes.
Oh, God.
How many of these do we need?
Quite a few.
And they need to be the size of ping pong balls to fire them from Jim and Craig's gun.
Can I have a go?
Yeah.
Right, dip it in here. Fairly quickly into there. That's it.
Yep.
Look at that. It's already the size of a pea. I'm just suggesting we probably need to find a way of mass producing these. I mean, this is the land of Henry Ford.
Right.
1 is good. We can try 3.
And now you've tripled your efficiency.
Haven't I? Haven't I? Sometimes on TV we don't do things in actual time. This is one of those occasions.
You gonna do anything?
Reading this.
There's no words, you're just looking at the pictures.
My turn again.
Yes.
Oh, you've been busy.
Hail's ready.
They're done.
They are done.
Magnificent they are as well. Look at that.
Okay, they might need a little bit of rounding off to get them down the barrel of the gun, but the size is good.
Say goodbye.
1,
Excellent.
2.
3 of 30.
We're gonna have to do some more, aren't we?
Really?
Yeah, okay. A whole bunch. Yeah, okay.
So we have something to compare them with. We've also frozen some water into ordinary ice, using a few of Craig and Jim's spare ping pong balls as molds. So we've got solid ice and we've got hail, which is ice in layers. Time to put them up against each other to see if there really is a difference. And we can't resist starting with one of our homemade hailstones.
I'll give you the honors. All you have to do is punch it.
Let me scoot back a little bit so we can look
Why
at
is
the-
everybody else standing back?
Well, I'm getting so we can see.
Right. What? I've not done this before, have I? How wrong can it go? Are we ready?
Yep, we're ready.
Punching a hole in there now. Oh, it's quite dramatic, as it turns out. Yeah, let's have a look at the footage.
Believe it or not, we're breaking new scientific ground here. So to make sure we capture any differences between the ice and the hail, we're recording everything at ultra-high speed. And sure enough, our cameras capture every detail, from the plastic seal popping off the tube to our hurtling hailstone punching through the target.
Oh, look at that.
That is awesome.
Beautiful.
Is it worth experimenting now with just seeing how much more resilient one is than the other?
Yeah, we brought plenty of materials we can shoot at, so we can actually shoot 2 of them at the same thing and see what one will go through, one won't go through, and the type of force that we have in there.
That's exactly what I was meaning. Do that. Right, let's
right.
do it.
So here's the setup. We've got lots of different sorts of wood, and we're going to take 2 shots at each piece. First with plain ice, then with our homemade hail. First up, chipboard.
Right.
3, 2, 1.
Ice, straight through. Hail, straight through. Okay, slightly thicker piece of chipboard. Same result. Plywood. The ice barely dents it. Come on, hail.
3, 2, 1.
Well, there is a difference. The hail splintered the back of the plywood. Let's try a slightly thinner piece. This time, the ice barely makes it through. The hole it makes is far smaller than the projectile itself. Right, fingers crossed.
Woo, nice.
It's awesome.
Did it work? What happened
It
at the
did.
other end?
It smashed, and there's your impact.
Yeah, well, that's right the way through.
Yeah.
Yep.
In fact, that's completely different.
Same piece of wood, same shooting speed, different results. In slow-mo, you can clearly see how much of the ice ball never makes it through the board.
Well, it might be crude, but that is what I hoped we'd see. This mark here, that's from the straight ice, barely getting through. That is our homemade hail with its laminated layers around it. Clearly, a more fearsome projectile.
Both balls are made of frozen water, so you wouldn't expect any difference in how hard they are. But the layers in hail do appear to make it stronger. So summer hail does seem to be harder than winter ice. But water can shapeshift into something even more dangerous. Naturally quicker than hail, with a mightier punch than hail. And what it is might well surprise you. This is how most of us are used to seeing snow move. Delicate flakes floating gently down to earth. Floating so gently that a snowflake can take nearly an hour before it finally reaches the ground. Traveling at just 4 miles an hour, little more than walking speed. And yet snow can be the fastest form of water that there is. Because when it's in an avalanche, it can hit 80 miles an hour in 6 seconds flat. And then, well, it just keeps on accelerating. The fastest one ever recorded on Mount St. Helens in America clocked a staggering 250 miles an hour. So how can snow move down a mountain faster than water can? Walter Steinkogler of the Institute for Snow and Avalanche Research is trying to find out how that incredible speed is possible by starting an avalanche of his own.
Walter, yes, is this where it's going to happen? That's
Absolutely, absolutely. You can see it quite nicely now. This is the
Yeah.
whole slope. You see 2 spontaneous avalanches already, and we're gonna try to release the avalanches from the very top.
Well, don't those 2 avalanches mean it's already happened, it's all over?
No, not at all. You see there's plenty of snow still on the slope.
Okay.
And actually this is a really good indicator for us that there is the potential to produce nice avalanches.
And then when that's going on, you're going to be conducting experiments and
Yes.
learning. I mean, this is part of an ongoing piece of work for you, isn't it?
It is actually part of my PhD thesis, and this data is really essential for my work, yes. you can
Right.
see.
There are several different types of avalanche, but the fastest by far is what's known as a dry powder avalanche. And that's the type we're hoping to get. If he can trigger a dry powder avalanche, Walter can find out more about how they move so fast. And we've offered to help by putting a barrage of slow-motion cameras on the slope.
We're not going to mess up your PhD.
I will tell you afterwards, but I would appreciate if you don't do that.
I will. If I do, send him the bill.
Oh,
He's the
I
director,
sent to this
There's
guy?
Graham there.
Perfect,
Yeah,
yes, I will do
He's in charge. I'm not.
Let's hope it doesn't come to that. but I would like to add an extra element into his experiment.
So, Walter, can I place these on the slope? If they're a known distance apart, I thought I could time when the front, the head,
We call it the front.
the front of the Avalanche passes one of these.
Yes.
I can time it over that distance and I can work out how fast it's going.
Sure. That's a nice approach. You can do that, yeah?
Thank you very much. Right, we'll do it. I just need a helicopter.
Okay, well that's that sorted. But now we need to work out how to fly our fences into precise positions without triggering an avalanche ourselves. Our safety team have been thinking long and hard about the best way to do it. And what they've come up with is dangling someone on a bit of rope. This someone, in fact, who apparently enjoys this kind of thing.
That is the single coolest thing I have ever witnessed. That man is without a doubt the best helicopter pilot I've ever seen in action.
I mean, that sky sponge was difficult enough.
Just to be flying that close to mountains and sheer rock faces in this gusty, windy, changeable weather. Just that, let alone with another bloke dangling from a piece of rope below you, and then below that a huge, well, basically wooden sail. Speechless, genuinely speechless.
Walter has told us where he expects the avalanche to fall, so we position the first fence slap bang in its path. But the conditions up here are very changeable, as we discover when we try to fly the second fence in. Suddenly, the winds quicken and start to gust alarmingly. At any moment, the whole fence could be dashed into the side of the mountain, taking that bloke with it. Not to mention the helicopter. And the fence needs to be exactly 100 meters from the first one. Never have the words "rather him than me" been more directly applicable. It's down.
So everything is now in place. My two boards I know are 100 meters apart. When the front of the Avalanche passes the first one, I'll start the stopwatch on my phone, stop it when it passes the second, and we'll get an idea of the speed. And I do know we're going to be surprised how something that a little snowflake can take an hour to drift down out of the sky can suddenly be part of something so fast and so powerful.
All we have to do now is wait for them to trigger it.
That obviously is the explosive.
Okay, we're off. Fence one, fence.
Oh. Well, my boards have gone.
missed it. But I suppose it does prove, in a way, just how fast an avalanche can be. And luckily for me, our slow motion cameras captured everything. So let's take a look at that avalanche again. This is the moment the dynamite is dropped from the helicopter, causing this explosion at the top of the mountain. Immediately it's surrounded by a powder cloud, made up of 1% snow and 99% air. This is a dry powder avalanche. The avalanche accelerates down the steep incline until it reaches our first fence, though not exactly at the angle we expected. The leading edge passes the first one now, and that particular bit of snow reaches the second fence now. Almost exactly the same time the first fence is destroyed. No wonder I had trouble timing it. Our avalanche was actually only travelling at 25 miles an hour, just a tenth of the speed of the fastest one ever measured, but still faster than if we'd just pushed that snow over a cliff. I want to know how that's possible.
Let's imagine there's a chunk of snow at the top, and then it starts to move. What's happening to that snow from the moment it starts to move down?
Well, first it will break into pieces and it gets rounded a bit, and it also gets compressed.
And these are the pieces which you can see up there. They look like snowballs.
Technically, most of them are snowballs, yes.
These snowballs are the secret of what's going on underneath that powder cloud. Walter offers to show me how.
Okay, Walter, this is like an avalanche. How?
Well, you imagine an avalanche that's moving down a slope. It's gonna pick up snow like you are doing now, and it's gonna put it in motion, as in our tumbler here. It seems you're losing your motivation. Come on, keep on going. One more. You can do it. You can do it. Come on, Richard. Perfect. I think we're good there. And you can see already it's compacting, then it's breaking apart again, then it's compacting again, and at some point you will end up with ball-shaped features.
It is magically making
Snowballs.
a cement mixer full of snowballs, yeah.
It makes snowballs. Of course, in an avalanche, this is happening much faster, and it's much more violent process going on there.
But this is a slowed down version of exactly the same process, and you can see that sort of grinding, rolling motion you can imagine happening.
Perfect. Yeah, that's exactly the case. Yeah, true.
So understanding this will allow you to understand more about how fast it might go, where it might go, how it will behave.
Absolutely. I would say they are quite done. Yeah,
Can I turn it off?
Perfect. Yeah, turn it off, please. Yeah.
So in here, snowballs.
Perfect snowballs, right? Aren't they?
I mean, that's seriously packed.
It's quite hard, right? I mean, it would be not that nice to throw it on a person, I guess, this one.
Are you looking over there and thinking targets? Because I was. That's
Oh,
wrong.
they're cross-country runners?
Yeah.
Come on, do it. Come on, do it. He was scared for a second. Did you see?
Walter wants to excavate the avalanche to see how much snow it contained. And I follow him into, well, a big hole. Because I want to be sure whether it's these snowballs that make the avalanche move so fast.
This is not that easy to answer because still going on ongoing research, but for sure it defines the motion of the avalanche, yes.
So you can't say for definite yet as scientists, and I love it when you guys can't give a definitive answer.
Yes,
It's
I
great.
cannot
You're in a
because
corner.
it's my research, and if
Yeah.
I say it now, I mean I need to publish this stuff first.
So would you ever end up with your avalanche effectively rolling along on like ball bearings, or like when they used to build, they'd get a huge stone and move it to one place to put it up as a monument. They'd roll it along on logs, wouldn't they? Is it like that?
I think you can kind of say it like that, yeah. I'm from a scientific point of view, I'm not 100% sure.
You
I
think
have to
that's
admit.
rubbish, don't you?
No.
Be
I'm not saying-
honest.
no,
Come
no,
on,
no,
you
I'm
big
not
old
saying-
you go,
no.
from a scientific point of view, I'm not sure. It just says rubbish.
No, there are studies that say that really it's the ratio between the bigger grains or the bigger balls to the smaller balls that can significantly influence the speed and the motion of the avalanche. So you're not that far off, actually, with your
Maybe
comparison.
you're just jealous because it was my idea.
Yes, I know. but yeah, no.
That's what it is.
You can publish that, actually. That would be something for
But I have to write it up.
Yeah, but you can go into research.
I can't be bothered, take ages.
No,
You can
no,
have it.
no,
Have
no,
it. It's yours.
okay, then I
It's
do
yours.
it.
Yeah, have it. It's yours.
Put something on wheels and it can accelerate quicker than if you simply drop it. And these snowballs may be the wheels of a dry powder avalanche. Snow is the softest, lightest way that water can fall to Earth. But an avalanche can move faster than any other type of water. 4 times faster than the fastest flash flood ever measured. And it seems snowballs might well be the secret. Of all the water on our blue planet, only a tiny fraction is actually in the atmosphere. Yet water's incredible powers of transformation mean that that's enough to bring us all our clouds, rain, hail, and snow. And with it, all the everyday weather on Earth.